looks normal. All right, so let me explain what we've got here. We have a circuit that has a source, and the source has a voltage that's described by this function right here. So it's not DC, so we can't use our DC equations. We can't use that table that has all the alphas and the omegas because it's not a DC circuit.
AC plus step or something?
Yeah. Whatever it is, it's something that you say, okay, well, I'm going to have to take a Laplace transform on this. And it's got a resistor and it's got a capacitor. So we know we need to first put everything into the S domain. So we want to, first we'll start with taking the Laplace transform of our voltage so that we've got that. This is not a step you will often have to do, but you might. So you need to remember that the Laplace transform of a constant is 1 over s. So the Laplace transform of 2 over pi is 2 over pi s. So it's 2 over pi times 1 over s. And then if you have another function, if it's got it multiplied by a constant, that's okay. You can just leave that constant alone. So I can leave the 4 over 3 pi alone. And now I need to get the Laplace transform of cosine 2t plus pi. So I need to get a table of Laplace transforms, which there are no shortage of those until you want one. Do you happen to have yours handy? So, like from class. Oh wait, there was one on this PowerPoint. Okay, so we have, first of all, it had something added to it, so we may have to come back here for this time shift, but let's look at, those were properties. Do we have the functions? No, of course. I said Liz is just like the examples, like we have it until we need it. Oh, he's answering a different question than I am. Okay, that's okay. That's
Is it this stuff?
It is that stuff. So what I'm looking for is cosine. The cosine on the left.
Cosine.
Cosine
omega
AT plus omega.
Okay. So I have. Oh, AT plus omega?
What does it have?
I see cosine omega t plus
Oh, that's fine, yeah. Omega t plus
theta or something.
plus theta. That, perfect. Okay.
Times u of t.
Times u of t, perfect. Yep.
And I got s cosine theta minus omega sine theta over s squared plus omega squared.
Is that it?
Yeah. That's what I have.
Okay. That's not what I was hoping for.
Oh, okay.
No, but that's okay. That's what it is. All right. So the Laplace transform of this function up here will be 4 over 3 pi s cosine theta, not, well, theta is pi, s cosine pi, minus omega is 2 sine pi. Oh, this is going to work out because, yeah, pi, yeah, this will work out. S squared plus 4. OneNote hadn't been doing this to me lately where it refuses to scroll. I don't know why it does that sometimes. And I just have to like keep adding little bits so it'll scroll a little bit. Okay. Is everything okay with that? Okay, applying the Laplace transform. All right, so now if I come on.
There's a little minimize thing. See a little, yeah. Does that do anything?
It does, but it doesn't help.
No. It's weird.
Yeah, it's a weird thing that has been going on with this computer and this, and with OneNote, pretty much since I've had it. And it did not help. Now can't even find where the problem was. Where is it? Okay. All right, so now we've got the Laplace transform of our voltage source. So that was, can you read it out to me?
So it's 2 over pi s plus 4 over 3 pi, and then big bracket s cosine pi.
Okay, what's the cosine of pi?
0. -1.
-1.
So negative s.
Negative s.
Plus minus 2 sine of pi, which is 0.
Right. That's why when I saw that I said, oh, this will work after all, because I was afraid it was going to be yucky.
So, and then over s squared plus 4.
Right. And so when I saw what the Laplace transform was, I said, oh, that's not what I was hoping for. It turns out not to be as unpleasant as I was afraid of. So that's our voltage source. Now we have a resistor, and what is that going to be in the S domain if our original resistance was 15 ohms?
It'll be the same thing.
It'll be the same thing. And usually when you transform to one of these, I don't know if this is for sure in the S domain, but usually when you transform to one of these domains where everything acts as resistors, then you say call all of these things ohms.
Oh, really?
So 0.2F, that's a capacitor, and so capacitor, the Laplace transform of a capacitor is 1 over SC. So this would be 1 over 0.2 S. Now we have to see if it had any voltage at time t equals 0. And if you look at our voltage function, it had a unit step function at the end of it. And so we know it was 0 until we got to 0. And so if it was 0 before, the capacitor did not have any voltage ahead of time, so I don't need to add that extra little voltage source.
Okay.
So 1 over 0.2 S is the same as 5 over S. And I didn't tell you I didn't give you a problem for this. Let's have our problem be to find IC of t, find the current through the capacitor as a function of time t. So we'll do KVL. You usually will be doing KVL, and I would have minus 2 over pi s plus 4 over 3 pi times minus s over s squared plus 4 plus 15I plus 5 over s I equals 0. And then I take everything that doesn't have an I in it to the other side. So I have, and I'll factor out an I from what's left. So I have I times 15 plus 5 over s equals 2 over pi s minus 4 over 3 pi s over s squared plus 4. If you need to go, that's, just let me know.
It looks like we're coming to a conclusion with this sticky.
We are. All right, so then this I will equal 2 over pi s over 15 plus 5 over s minus 4 over 3 pi s over s squared plus 4 times 15 plus 5 over s. So now, if I multiply by s over s, I get 2 over pi over 15s plus 5 minus 4 over 3 pi s squared over s squared plus 4 times 15s plus 5. So on the second fraction, when I multiplied by s over s, when you multiply three things together, associative rule says you can group any two of them together, so I multiplied the s times the second one. Because if I have a times b times c, that's the same as if I do a times b times c, or a times b times c, or I can even do a times c times b. So people want me to distribute it through both parentheses, but you don't do that because they're multiplied, not added.
Because then it'd be like c squared.
Right,
like
right. You distribute over addition, not multiplication. Okay, so our first fraction is good to go for taking the inverse Laplace transform, because if I take a 15 out of the denominator, I'll have 2 over 15 pi times 1 over s plus 1/3. And for the second fraction, I'm going to have to do a little bit of work. I've got an s squared. I took a 15 out of the second set of parentheses, and that gets me s squared plus 4 times s plus 1/3. That is not ready to take the inverse Laplace transform of, because I have this product in the denominator. So I have to do partial fraction decomposition on this. So I'm going to say s squared equals s squared over s squared plus 4 times s plus 1/3. And that will equal a plus bs over s squared plus 4 plus c over s plus 1/3. Now where these came from is for any factor that is linear, you just have a number on top. If it's a quadratic, you have a constant plus bs, or you have a constant plus a linear term.
Saw that somewhere.
And if you had multiple linear terms, I would have like if I had s plus 1/3 squared, I'd have c over s plus 1/3 plus d over s plus 1/3 squared. So now I know, I'm trying to find these coefficients. So I know that s squared over s squared plus 4 times s plus 1/3 equals, and if I got a common denominator here, I would have a plus bs times s plus 1/3 plus c times s squared plus 4 all over s squared plus 4 times s plus 1/3. So I multiplied the first fraction by s plus 1/3 over s plus 1/3, and I multiplied the second fraction by s squared plus 4 over s squared plus 4. And then I had common denominators, so I could put them together.
Okay.
You sure that's okay?
It's there.
Do you want to write out that step, or do you want me to? Okay.
No, I can.
You can figure it out.
Yeah.
So this is as plus 1/3 a plus bs squared plus 1/3 bs plus cs squared plus 4c. And all of that has to equal s squared because the denominators on both sides of this are the same. So I can just ignore the denominators. So now I'm going to gather these together based on their s, their power of s. So I have cs squared, and I have more than, I also have a bs squared. So for s squared, I have a c plus a b. For s, it looks like I just have a b. No, I have a b and an a. I have a 1/3 b and an a. And for my constants, I have a 1/3 a and a 4c.
Constants.
Okay, so on this side, I have a 1s squared plus a 0s plus a 0.
Okay.
So 1 equals c plus b, 0 equals 1/3 b plus a, and 0 equals 1/3 a plus c.
Oh, that's handy. Okay.
So I have that a equals minus 3c from the bottom equation. I can plug that into the second equation, and I get 0 equals 1/3 b minus 3c, or b equals 9c.
That bottom one, should it be 4c?
It should be, thank you.
Sorry, I wasn't.
No, I didn't want to go any further with the mistake. So 1/3 a plus 4c. So from the bottom one, I get a equals minus 12c. And then from the second one, I get 0 equals 1/3 b minus 12c. Did I make another mistake?
Oh no, you just plugged in 12C.
Yeah. And so b equals 36c. So 1 equals c plus 36c. So c equals 1/37. I was expecting nicer numbers than
I
this.
got something different.
Okay,
12.
let me try. I probably,
So at 0 equals a plus 1/3 b, is that right?
0 equals a plus 1/3 b, yeah.
And then I stuck in negative 12c for a.
Negative 12c. So add 12c to both sides. 12c equals 1/3 b.
And then b equals 36c.
C. That's what I got.
Oh, okay.
And then I plugged into the first equation. So I have 1 equals c plus 36c. So 1 equals 37c. So c equals 1/37.
Which is a weird number.
It is a weird number. And so b equals 36/37. And a equals negative 12/37. So that means that this second part of our thing that we're trying to work with the first part is still 2 over 15 pi times 1 over s plus 1/3 plus 4 over 45 pi times what was a?
Negative 12/37.
Negative 12/37 plus b
36/37.
36 over 37 s over s squared plus 4 plus and then what was c?
137.
137 over s plus 1/3. Okay, so it looks terrible. It's actually not as bad as it looks. It's almost ready to take the inverse Laplace transform of. So if you look at this, the s squared plus 4 term, and you go to your Laplace transform tables, which I don't have up here anymore, find the one that has something plus s, has s squared plus something in the denominator. S squared plus omega squared or something, s squared plus.
So I see omega over s squared plus omega squared.
Okay, so we have that one. So s, you have omega over s squared plus omega squared, and you have s over s squared plus omega squared.
Yes.
Okay, so for the omega over omega squared, omega for us would be 2. So I'm going to do this quickly. So 4 over 45 pi times negative 12 over 37 times 1 over 2 times 2 over s squared plus 4 plus 4 over 45 pi times 36 over 37 times s over s squared plus 4 plus 4 over 45 pi times 1 over 37 times 1 over s plus 1/3. It looks terrible, but everything I'm about to circle is just a number that you just calculate. That's a number, that's a number, that's a number, that's a number. So I have some number times 1 over s plus 1/3 plus some other number times 2 over s squared plus 4 plus some other number times s over s squared plus 4 plus some other number times 1 over s plus 1/3. Oh, which actually means these two together are just some number times 1 over s plus 1/3.
And then the ones in the middle are the same?
Yep. And the s 1 over s plus 1/3, so that'll be some number e to the minus 1/3 t. Then the 2 over s squared plus 4 will be some number times cosine 2t. And the s over s squared plus 4 will be some number times sine of 2t. And that's it.
Wow. Okay.
Okay.
It just looks, it's just a lot of math.
It's a lot of math. To get one that doesn't have a lot of math, you have to have a very particular one. But when she puts one on